Good evening, and welcome back to Vegas October 1 Sounds. Tonight is our third episode in wave, sound, particles, interference, diffraction, you name it. So tonight we're going to go and explore the slits simulator. And in this case it's a little bit different than the others. It's not showing particles like we did before with sound. Well, let's see what it actually does do. Yeah, it doesn't allow us to show the little particles. What it does is generate a line source. Now remember, we've been talking about point sources as representing muzzle blasts on my channel. We've been talking about cones to represent the shock wave front, and I've mentioned continuously line wave fronts. This is an example of a line wave front. So if we turn it on, we can see that it generates waves that are parallel or perpendicular, however you want to look at it, to any particular edge of this experimental square. So in this case, what we're going to do is explore what happens when a wave meets with a barrier that has a hole in it. And in this case, we call it a slit because we're just looking at it from a two-dimensional thing. And we can vary the width of this slit. And in this case, for sound, we can vary it from 20 centimeters, which is, let's see, 20 centimeters divided by 2.54, a little less than 10 inches. Or we can go all the way up to 160, which would be quite a big thing. We can also move it left and right to give us a little bit more working room or see if there's any effect there. All right. So let's go ahead and get started. We'll set it down to the lowest possible frequency, about 100 Hertz, and we'll look at this. As we can see, with a small slit, even though we have a max amplitude signal to the left of the slit, not much of the sound pressure makes it through. We could bring our little tool down here and measure it on both sides. So there we see we get pretty good amplitude, but if we bring it over to the right, amplitude is substantially reduced. And of course, now let's explore the amplitude going up, but in this case we want to compare it to right there. So as we go up along the edge of the barrier, we can see that the amplitude drops off pretty drastically. So for a small slit relative to the width of the high pressure zone, most of the pressure is going to be directed out away from the opening of the slit. And if we go over here, you can see that it's a greater amplitude. And as we go up, you can see that it's going to be, in that case, once we get away from the slit, then the pressure tends to even out. But up close to it, the highest pressure occurs there, and that high pressure just doesn't quite seem to propagate along the edge of the barrier. Now, in acoustics, we have a concept known as near field and far field. And where the position of these calipers are right now would definitely be near field, and as we move them out and further away, it would go into intermediate or far field. So you can see that depending upon the location of where you're at, that will substantially alter the intensity and perhaps even the shape of the waveform. In this case, though, not so much. All right, that's one slit, a narrow slit at low frequency. Let's go ahead and up the frequency to the max and see what happens. Okay, well, the frequency looks to be preserved. And as we had before at these locations, the pressures seem to be pretty constant across everything. But if we move our white meter in, let's see what it is. Once again, you see that very close to the opening, the pressure is pretty loud. Along the edge here, it gets substantially smaller and smaller than it is one would go out away from the barrier. So along the barrier, as you can see by the little grayish area in here, the pressures don't correlate well in terms of the amplitude to, well, correlate is a bad word. They don't reach the same maximums as and minimums as other portions of the pattern out here. And as you can see with the gray area, both top and bottom, that's where these lower zones of pressure are. Alright, so this is all as expected, and we see that regardless of what frequency we have, that frequency is pretty well preserved on the other side of the opening. So what can we say? If you have a window that's small and you have a sound that's low frequency, then the sound escapes through the window, and in so doing it only emits a portion of the total intensity of the energies on the upstream side of the window. And you know, that's kind of what you'd expect. You know, you play your radio loud in the car with all the windows rolled up, it's a heck of a lot softer to the guy walking on the sidewalk next to you than if you have all the windows down. Kind of the same phenomenon. No way for the pressure to directly escape. It has to first vibrate the glass, and then the glass vibrates. And it seems to be, at the moment anyway, independent of frequency. So let's put our frequency back down, leave our amplitude max, and let's move this over to the left a little bit, and up the slit width. Now you notice that we still have kind of concentric circles, but if we up our slit width to say half that distance, we start to lose the concentric circles in the near field region. In the near field region, the waveform on the outside of the opening is kind of straight up and down, and then it soon dissipates into this semicircular thing again. And as we reach the maximum width of the single slit here, but it's the same thing, except that the up and down can propagate out further before it becomes truly concentric circles. And we'll also notice here that with the wider slits, this zone of quietness has expanded to a much greater region of the upper and lower portion of the outside of the slit. Alright, now, so let's get this thing out of our way and just make some qualitative observations. Now let's up the frequency on this big old wide thing and see what happens. You'll notice that it doesn't curve quite as much as quickly. In fact, it almost looks like straight lines going straight out, and then the volume decreases substantially in this region, and as it does, it curves. So observation is that as the aperture size of the slit grows large compared to the frequency, then the waveform preserves its shape. And let's look at that waveform. And we can look at that waveform. Now we still see that it has an up and down sinusoidal thing, but if we measure it up there, well, we can't do a good job here because we only have a two-dimensional view. But anyway, you can see it. It's linear or straight across for a much larger region of the screen. So higher frequency through a large opening relative to the size of the wavelength of the sound, you tend to preserve a little bit of the shape of the original wave in the near field, and maybe even out into portions of the middle field. For a small slit, no such deal. It acts as a point source, regardless of the frequency. So when the aperture is small relative to the wavelength, you get the resulting waveform is that of a point source. When it's large, it's a combination. And directly in front of the opening, for quite a distance, you get something that's a mixture of a point source and a combination of the original waveform and modified a little to look like a point source. So, how does that apply in Vegas? Well, theoretically, shots were coming out windows, and sound was coming out of windows. So you have to look at the frequency of the sounds being emitted, which for gunshots are broadband, or for the muzzle blast, a little less so, compared to the size of the hole to determine which type of pattern you're getting. And you have to be careful when you make calculations. So yet again, there's another complication when you're talking about what happened in Vegas. Now this is all fine and dandy and easy. We got one width. What happens when we have multiple slits? Let's go to a two-slit situation. All right, so we've got one source of sound. We've got a two slits now, and all of a sudden what we're seeing is the waveform that we see when we had two sources of sound. Namely, the line source comes, hits the opening at top, hits the opening at bottom. They both appear as a coherent point sources, and they interfere, producing the standard interference pattern that we would expect from previously. This is with a small aperture, even Mach frequency, with low frequency. Same thing happens, it's just that the pattern, as we're used to by now, is much smaller. Or, excuse me, much smaller, much larger in nature. Alright, so what happens when we increase the slit width? And of course, we can also play with the slit separation here. We'll do that in a minute. But let's explore the slit width first. So if we increase the slit width where we had these semi-straight lines, in this case you can see that most of the energy is escaping from the left side of the barrier, and hence most of the shape of the wave is preserved, and the curvatures only occur on the ends where there's interference, constructive and destructive, from the other opening. As we up the frequency, of course, it's more pronounced. So when you have two large slits separated by very little distance, and the slit size is large relative to the wavelength of the sound, then you get a pretty good preservation of the shape of the waveform. In other words, these are pretty much still straight up and down, but not quite. And as we increase the separation between them, let's go way out here, then we start to get a little bit of some interference patterns here behind the barrier until the sound can come together again. So as I had alluded to earlier with 2 point sources, directly behind a light pole, I said you kind of got some sketchy business going on. And I said it will tend to look like interference patterns, and then at distance it will come back together and almost be the same as the original one. And this is an example of that phenomena. So we have two large slit widths, large separations, high frequency, and we observe that even though the barrier size here is large compared to the wavelength of the sound, it still kind of moves around it. Now if we reduce the separation down to minimum, like that, this would represent a situation where you have a light pole which is small compared to the wavelength size. So let's put the wavelength size way down, and as you can see, when the sound moves past the wave pole, there's very little disturbance whatsoever. So in the case of low frequency, hitting a light pole where the wavelength of the sound is much larger than the width of the pole, that's what it looks like. But as we increase the size of the pole, which in this case is simulated by increasing the width of that, let's say it's rather than a pole, it's a car, and just let this thing run. Okay, then here you start to see some constructive and destructive interference, and on the other side of the car, even those lower frequencies tend to create a little bit of a dead zone until the pressure can push itself back in there. At high frequencies, that let's say car size thing, definitely has an influence, a much larger influence, shall we say, although it still overall at distance wraps, eventually fills back together, and it's as though the car was not there. So you can see that sound is pretty flexible, and that with this little gadget you can experiment around it and do a lot of little things. If we were to let's see, we've got everything maxed out now: frequency, amplitude, slit width, and distance. And you can see that we're once again, with the aperture size large, you tend to get a preservation of the waveform of the from left to right. And then when it hits this large obstacle, even though it's a higher frequency, in fact, because it's a higher frequency, it tends to get the interference behind it, and if we reduce the frequency, it would tend to just, kind of be less involved, just kind of bends it. And that's how sound moves around objects, by constructive and destructive interference. And if we make it the size of a pole, that object in the middle, then the effect of that becomes less and less until, way down here, there's nothing. There is something there, it just goes all the way straight through. All right. So that's the basis of how sound passes around objects. It's the basis for how sound passes through windows or objects that are open, over walls, over buildings, around buildings, through buildings where there's an open thing. Alright, so now let's see if we can do something technical and measure the amplitude of these things. Alright, if we bring down our measuring tool here, and we measure the amplitude of the wave before it passes through the slit, and then we measure the amplitude of the wave, say out here where it's bright, you can see that even though this low frequency had to pass through a substantial size object, it still at a distance preserves the amplitude that was on the left side, as though there was really nothing there. But it did change the time of arrival to a different pattern. So time of arrival is modified when sound attempts to pass around objects. And that's a crucial factor also. If you're measuring the arrival times of either the muzzle blast or the supersonic crack, after the sound has passed around an object, it's going to be longer than if you had a direct line of sight to either. Not by much, but enough to be noticeable if you're doing precise measurements. And by noticeable, I mean if you're doing 1 millisecond measurements of either of those, then it's possible to notice when sound goes around an object if the object produces enough delay. For small objects, you'd probably have to have a much finer granularity to observe it. Okay, what else can we say? Well, that covers the basics of this, and I encourage you to play with this, to think about it, to apply it to Vegas, and come up with your own understanding of how sound works. What else? Okay, let's move on now to the final section of this, which has very little to do with sound whatsoever, because the scale needed to represent this stuff is far larger than we have. But I will tell you this: these things which I'm going to show you with light can have an impact when you look at the Vegas setting as a whole, because the sounds have to go over and around and under and through objects, and in so doing they create these little interference patterns, and the look of those interference patterns on the downstream side can often resemble things that I'm going to show you here with light. So in this case we have a coherent set of light, a laser, and we turn it on. In this case it's green. Let's go a little bit down further blue, and we're going to pass it. There's a square here which contains small openings, and the openings are in nanometers. The wavelength of light is on the order of hundreds of nanometers. The opening is on the order of a fraction of a nanometer, and the eccentricity we'll get to in a minute here. So that's the size of the opening, but it really is quite small if you look here up in here compared to the wavelength of light. All right. So what happens when we pass a beam of coherent light through a very small opening, and the opening is round, projected onto a dark surface, or a light surface if you want? What we will see is interference patterns created by constructive and destructive interference that look like this. As we increase the diameter of that opening, you'll see that the middle portion shrinks, but there are more concentric rings. And this is because of what happens with the interference. And that's kind of got a cross in the middle. With the larger regions here and the number of light waves here, you get more possibility for constructive and destructive interference, and therefore more pattern. So let's try it this time. Rather than with a circle, let's try it with a square aperture or opening. Ah, kind of pretty, isn't it? So rather than get circles now, we get two lines. And as we increase the width of that square aperture, the lines shrink down, just as they did with the circle. And here we can change the width and height until they're equal or whatnot. What about if the aperture, rather than being a square or a circle, contains both? So here we'll get a mixture of both. We'll get the cross formed by the square, and we'll get the circles formed by the circle, and they'll cross interference and produce these diagonal lines. And as we increase the diameter of both, you can see what happens here. And then as we increase the width of the square, you can see more of the square effect comes into play. That's all good. All right. What if we have, rather than either of those, we have this? We have a matrix of circles. Then every little circle gives more opportunity for interference, and the black regions block the light. So you get basically a composite of what these small circles would be, which kind of looks like this. Alright, and if we increase the circle's diameters, then the output gets more refined and they turn to dots. As we do that, as we decrease the diameter of the openings, then you get this. And this is quite useful in real life if you want to look at the structure of transparent crystals, or look at crystalline structure. You can use a laser to get this type of thing. Or if you want to look at non-transparent, you can use X-rays, and the same phenomena happens, provided that the X-ray is of the proper frequency and orientation to the size and structure of the lattice. Alright, now the last thing we'd like to mention here is what happens when you have just some random object. And we can see that there's nothing in particular there. As we increase the size, of course, the patterns get smaller but more detailed and varied, and we can rotate it and watch what happens. Alright, now let's go back, and rather than to this circle, there we are, and we're using blue light, which is a shorter wavelength. Let's go over to the red light, which is larger wavelength. And as we go up in frequency, then you'll see that the circles increase. And that's very much like what happens with the sound when we had the constructive interference. As the frequency goes up, the interference pattern changed also. In this case, not quite in the same fashion, but in an analogous manner. Alright, so that's enough playing around with that. I think that we're pretty much done with this series of slides. And you can see that when you're thinking, talking, visualizing, and analyzing sound, that it's not a straightforward phenomena by any means. And when you consider all of the reflections, objects, and general construction of the venue, you can see that even without the complications due to the supersonic projectile, that just with the muzzle blast alone, there could be regions that are quiet because of destructive interference, and 20 feet away it would be loud because of constructive. Did I say destructive first? Destructive first, constructive second. And so as you're walking, even without the effects of the supersonic projectiles, you could still get this feeling that the bullet was chasing you, or that there was a shooter closer by than 20 feet earlier. It's not a straightforward process. Now, that's only if the sound is moving around objects. If you have a clear path with no ground and no reflective sky and no buildings and nothing, then it is a straightforward. You hear the muzzle blast will propagate out in a sphere, and one over the the square of the distance will determine the I don't know how to call it volume, but intensity of the sound that reaches you based upon your distance. But when you add real world situations where you have the ground reflecting, you have buildings reflecting, you have sound going around objects and all this, you have to start thinking in terms of these interference patterns. And you cannot say that if I am at the corner of, I don't know, Tropicana and the Boulevard, for example, and you're at one spot and it sounds loud, that's how it should be, because 20 feet away it will be soft because of the potential destructive interference pattern. Now, I make it sound complex, and it is, but by and large, since reflections are scaled down both in amplitude and time of arrival versions of the primary signal, it's not as complex as all that. But when the sound goes around objects, it is that complex. For example, if you're hearing the muzzle blast sound and you duck behind a car and you're right next to the car door, guess what happens? The sound can't quite reach you with the same pressure as it is on the other side. Therefore, the sound is going to be reduced or attenuated, as we call, in volume. And that's frequency dependent. The lower frequency muzzle blast will work its way down to you on where you're ducking and covering on the shady side, shall we say, of the car, but the high frequency won't. So ducking down behind a car will amplify the muzzle blast if the supersonic crack was generated upstream. Now, the complication arises when the supersonic crack is generated on the side of the car that you're on, which is very possible. Because remember, the muzzle blast is generated one time up at wherever the shooter was, and the supersonic crack gets continually generated along the path of the bullet. And based upon where you're located relative to the bullet trajectory, you could actually hear a supersonic crack that is on the same side of the car as you. So, position, or same thing as in real estate, location matters. And also the frequency of the sound and where you're at. And all these things come into play. And once again, I'll go back and say that I think the only person that I think that was right initially in the first couple of weeks said that to truly understand what was going on in Vegas from a sound perspective, you'd have to do a real complex 3D sound modeling simulation. And I think that's true. But on the other hand, when you're at a place and you record a sound and it's just massively dominant with one frequency or one event, then you can still take very precise times of arrival, and you can look at the frequencies, which in a spectrogram are fairly independent of intensity. I can see a percussive bullet going by amongst screaming, because the bullet is straight up and down, and the screaming is kind of horizontal. So anyway, It's complicated, but nevertheless you can still get some acoustic analysis done. But simple statements are just those. There's simple statements, rules of thumbs. You can't always count on them, so be careful when you're making assertions about what the sound should sound like when you haven't taken into consideration the full effects of reflections and refractions and all that. All right, that's it for this evening. We'll catch you in the next one. Vegas October 1 sounds out for the evening.